Silence. Not the quiet between breaths nor the pause after music fades, but a silence vaster than thought itself. A silence that stretches across the fabric of existence, swallowing galaxies, erasing memory, leaving only stillness where once there was fire. Imagine the last star, burning faintly in the depths of time. Its light flickers, fragile against an ocean of blackness. And when it finally dies, there will be no dawn to follow. No warmth to kindle new beginnings, only the endless cold, the eternal night. In this vision, time itself is stretched so far forward that it ceases to have meaning. There is no movement, no heat, no difference between one place and another. Every atom drifts toward equilibrium, until nothing distinguishes the here from the there, the now from the then. It is the end not with a bang, but with a whisper, a cosmic hush that never breaks. This is the heat death of the universe, the final destiny written into the second law of thermodynamics. A law that says entropy must rise, order must fade, and energy must disperse. It is not a violent destruction, but an exhaustion, the fading of all fires, the extinguishing of possibility. And so the question emerges, not simply when this silence will fall, but what it means. What does it reveal about existence if everything we know, life, thought, beauty, even time itself, is only a fleeting spark before the stillness? Perhaps the march toward silence has already begun. Perhaps the universe is already collapsing into quiet, while we live unaware, suspended within the slow unfolding of its final story. Long before telescopes pierced the night, long before equations etched their symbols into the sky, humanity turned to myth to explain the rhythm of creation and decay. In the hymns of ancient India, the universe was not a single story, but an eternal cycle. Hindu cosmology envisioned vast ages called kalpas, epochs of birth, growth, and dissolution, where the cosmos was created and destroyed in a rhythm too immense for human time to measure. Creation itself was a breathing, an inhalation and exhalation of Brahma, the cosmic order pulsing across infinite eons. To the Stoics of Greece, the cosmos was destined for fire. They spoke of ekpyrosis, the great conflagration that periodically consumed the universe, only for it to rise again, reborn in flame. In these myths, endings were not final. They were preludes to renewal. Time itself was circular, a wheel that never ceased its turning. But as centuries passed, myth began to give way to measure. By the 19th century, science had begun to describe the universe in the language of energy and heat. Clausius Kelvin and the pioneers of thermodynamics discovered a principle that shattered the old cycles: entropy. Entropy was more than disorder. It was the law that in any closed system, energy spreads, differences fade, and usable work diminishes. It was a principle as universal as gravity, governing steam engines, chemical reactions, and the very stars themselves. With it came a disquieting realization: if entropy was inevitable, then the cosmos too must be running down. This was the beginning of a new kind of mythology, one written not in poetry, but in equations. For the first time, science suggested that the universe might not be eternal. The second law of thermodynamics spoke of an irreversible march toward equilibrium, where motion would slow, structures would decay, and time itself might one day lose its meaning. The stars offered a sobering confirmation. In the mid-19th century, astronomers and physicists began to understand the nuclear furnaces that gave them light. Stars were not eternal lanterns in the night sky. They were engines consuming finite fuel. Each was destined to fade, to swell, collapse, or cool, leaving behind remnants that glowed faintly against the dark. Even the sun, so central to life, carried a hidden clock. One day it too would run dry. The heavens, once thought unchanging, were revealed as mortal. The sky was not a fixed dome of eternal brilliance. It was a story with a beginning, middle, and end. The 20th century would deepen this revelation. Albert Einstein's theory of relativity reframed the universe itself as something dynamic, woven from the fabric of space-time. Time and space were no longer eternal stages upon which events unfolded. They were part of the play itself, bending and curving under the weight of matter and energy. This was a profound fracture in human thought. Newton had imagined time as absolute, an endless river flowing at the same pace everywhere. Einstein showed instead that time was flexible, its rhythm tied to speed and gravity. Clocks on mountaintops ticked differently than clocks in valleys. The universe was not bound to a single tempo, but played in countless overlapping measures. If time itself could bend, could it not also end? The question lingered unsettled as the 20th century pressed forward. It was a Belgian priest and physicist, Georges Lemaitre, who dared to imagine the universe's beginning. Building upon Einstein's equations, he proposed that the cosmos had expanded from a primeval atom, a singular moment when everything, matter, energy, even time, was compressed into a state beyond comprehension. Skepticism surrounded him until Edwin Hubble raised his telescope toward the galaxies and returned with proof. In 1929, Hubble revealed that the light from distant galaxies was stretched, red-shifted, as if carried by an expanding fabric of space itself. The universe was not static. It was growing, rushing outward in all directions. This discovery was a revelation, for if the universe was expanding today, then yesterday it must have been smaller, denser, hotter, and traced far enough back, there must have been a beginning, the moment we now call the Big Bang. With that single realization, the myths of eternal cycles and the dream of a steady, timeless cosmos fractured. The universe had a birth. Time itself had a moment when it began to tick, and if there was a beginning, then there could also be an end. The discovery phase of this mystery was not gentle. It tore at the fabric of certainty that civilizations had woven for millennia. The cosmos was not eternal. Its stars carried lifespans. Its laws demanded decay. Its very space was stretching, carrying galaxies farther apart. Every measurement, every new observation whispered the same haunting suggestion. The universe was fragile. It had started once, from a fire beyond fire. And perhaps one day it would end, not in myth but in silence entropy, a word that slipped quietly into the lexicon of science in the 19th century. At first glance, it seemed like a technical measure, a mathematical tool for engineers studying steam engines and the flow of heat. Yet hidden within it was a revelation so profound, so unsettling, that it would bend not only physics but philosophy, time itself. Entropy did not merely describe the dispersal of energy. It carried within it a prophecy. It declared that all ordered systems, no matter how vast or how small, were destined to unravel. That heat spreads, energy dilutes, and every flame, no matter how brilliant, will one day sputter into silence. When Rudolf Clausius formulated the second law of thermodynamics, he spoke with the precision of mathematics, but the echoes of his words were existential. The energy of the universe is constant. The entropy of the universe tends toward a maximum. Hidden in that sentence was a vision of finality. The universe, that endless sea of stars, was not eternal after all. It was a system moving inexorably toward exhaustion. For the first time, scientists glimpsed a cosmic fate, not of fire and rebirth, but of stillness. A chilling paradox emerged. The laws of physics that had once seemed eternal now whispered of an inevitable decline. A universe that would not end in a cataclysmic roar, but in a long, suffocating silence. The realization struck deeply at the foundations of human thought. For millennia, philosophers and poets had envisioned the cosmos as cyclical, a grand wheel of creation and destruction. Hindu cosmology described endless kalpas, universes born, dying, and reborn in eternal rhythm. The Stoics of ancient Greece imagined ekpyrosis, a cosmic fire that would consume everything before igniting creation anew. Even early scientists often clung to the belief in a steady-state universe, a cosmos without beginning, without end, forever balanced. Entropy shattered those visions. It offered no cycle, no rebirth, no return. Instead, it demanded a future where all gradients vanish, where all differences dissolve, where nothing more can happen because nothing more can change. To many physicists of the late 19th century, this was a revelation laced with dread. If stars could not burn forever, if galaxies would eventually exhaust their brilliance, then the universe itself carried a built-in mortality. The second law was not just a law of physics. It was a sentence. The phrase heat death of the universe soon emerged, yet the name was deceptive. It spoke of heat, but in truth it foretold the absence of it, the flattening of all temperatures, the evening out of all energies. Not a fiery explosion, but a quiet extinguishing. Not the drama of apocalypse, but the infinite dusk of everything. This concept unnerved even the most rational minds. Lord Kelvin, one of the titans of thermodynamics, spoke of a future where the Earth must sooner or later become unfit for the habitation of man. He saw not just the end of stars, but the end of meaning, a horizon where thought, life, and history would vanish into the inert cold of equilibrium. The idea sparked debates that blurred the line between science and philosophy. Was time itself simply the measurement of entropy's march? If entropy always increased, then the arrow of time pointed only one way, forward into decay. The ticking of clocks, the growth of civilizations, even the beating of a heart, all could be seen as echoes of this deeper cosmic law. Some resisted the vision. The steady-state model still appealed to many, particularly in the early 20th century. Perhaps new matter was being created continuously, replenishing the cosmos, sustaining the stars, defying entropy's grim decree. Others looked to cycles. What if the universe collapsed and reignited in endless succession, defying final silence with eternal rhythm? But entropy remained relentless. It cared little for human hopes or metaphysical longings. Its mathematics was clear and its logic unforgiving. Every engine that ran, every star that burned, every living breath increased the disorder of the whole. Local order was possible, even wondrous, but it came at the cost of greater disorder somewhere else. A forest could bloom, civilizations could rise, galaxies could swirl into spirals of light, but behind the beauty, entropy was always keeping its tally. What terrified many was not simply that the universe would end, but how it would end. Explosions, collisions, and cataclysms could at least be imagined as climactic, endings with grandeur. But heat death offered something more unsettling, endlessness without event, a final state that was not an end in time but an end of time. For without change, time itself loses meaning. In the stillness of maximum entropy, the arrow of time dissolves into aimless silence. It was here that physics collided with human imagination. If all stories end in equilibrium, what is the purpose of beginnings? If every civilization, every memory, every achievement is destined to vanish without trace, does the universe hold meaning beyond the play of its own laws? The shock of entropy was not only scientific, it was existential. It redefined the human place in the cosmos. We were no longer citizens of an eternal stage, but brief actors in a play whose ending was already written. And yet within this terrifying vision, another paradox stirred. Entropy was a law of inevitability, but its very discovery revealed the brilliance of human thought. Out of fragile minds came an understanding that stretched across cosmic scales. The same law that sentenced the universe to silence was also proof of the human ability to glimpse its destiny. The 20th century would only deepen this shock. When Einstein reframed space and time as a dynamic fabric, when Hubble revealed that galaxies were rushing apart, when Lemaitre proposed a beginning to all things, entropy gained a new stage. If the universe had a beginning, a Big Bang, then its end was no longer abstract. It was real. It was inevitable. And so the unsettling realization lingered like a shadow at the edge of every discovery. If the second law holds true across the cosmos, then the universe is not infinite in its vitality. It is mortal. Its story, though vast beyond comprehension, carries a final page. That page is not written in fire, but in silence. Not in destruction, but in the gentle suffocation of possibility itself. The shock of entropy was the shock of endings. A reminder that even the stars, even the galaxies, even the universe itself, are fragile flames burning against the tide of inevitability. The second law of thermodynamics once lived in the engines of the Industrial Revolution, in furnaces and pistons, in the steam that drove the machinery of progress. But as the 20th century advanced, scientists began to ask, if entropy governs the rise and fall of a steam engine, does it also govern the rise and fall of the cosmos? The search for answers required measurements that reached beyond the Earth, beyond the sun, into the silence of the universe itself. Entropy, in its simplest form, is the measure of disorder, the spreading of energy, the leveling out of differences. On a cosmic scale, that meant asking, how is heat distributed across the heavens? Where is energy concentrated? And how fast does it thin into equilibrium? The first great clue came not from the stars we see, but from the radiation that lies between them. In 1965, Arno Penzias and Robert Wilson stumbled upon a faint, persistent signal, a microwave hiss that seemed to pour in from every corner of the sky. At first they thought it might be a fault in their antenna, or even the mess of pigeons nesting inside. But it was something far older, far deeper. This was the cosmic microwave background, the fossil light of the Big Bang itself. Here in the faint afterglow of creation, scientists found the universe's first great entropy marker. The background radiation was astonishingly uniform, the same temperature to 1 part in 100,000 across the entire sky. It was a signature of equilibrium at the largest scale, a reminder that the infant universe had already been sliding toward balance, even as galaxies began to form. Yet within those tiny fluctuations, those slight wrinkles in the heat map of the cosmos, lay the seeds of structure. Without them, stars and galaxies could never have emerged. Entropy was not simply destruction, it was also the sculptor of form, allowing matter to clump, to ignite, to shine. Still, the overall trend was clear. The cosmos had begun hot and dense, but it was cooling, diffusing, equalizing. From there, scientists turned to the stars. Every star is an engine of entropy. Its brilliance is purchased by the burning of fuel, a slow and inevitable conversion of hydrogen into heavier elements, of order into disorder. The lifetimes of stars could be charted as a kind of cosmic calendar, massive blue giants living only millions of years, smaller suns like ours burning steadily for billions, and red dwarfs persisting for trillions. But no matter their scale, every star is finite. The fusion stops, the light dies, the entropy tally grows. By the late 20th century, astrophysicists began calculating not just the fate of individual stars, but the fate of galaxies and clusters themselves. In these models, the future was written in epochs. After 10 trillion years, most stars will have gone dark, leaving only the dim embers of white dwarfs, the ashes of neutron stars, and the silent gravity wells of black holes. After quadrillions more, even those remnants fade. But black holes posed a paradox. For a time, they seemed to be the universe's loophole, regions where matter collapsed into a singularity, sealed off from the rest of reality, immune to the ordinary rules of thermodynamics. If entropy means disorder spreading outward, could black holes trap it forever? Then in 1974, Stephen Hawking delivered a shock as profound as Clausius's law itself. Using the principles of quantum mechanics, Hawking showed that black holes are not eternal prisons. Instead, they leak. Through a subtle process at the quantum edge of the event horizon, black holes emit faint radiation. Over inconceivably long timescales, they evaporate. This Hawking radiation meant that black holes are not the guardians of entropy, but its accomplices. Their evaporation adds to the dispersal of energy, ensuring that even the darkest objects cannot resist the second law. Given enough time, every black hole, from stellar masses to the giants at the centers of galaxies, will vanish, leaving only faint whispers of radiation as their epitaph. The vision was staggering. Not even the universe's most fearsome objects could escape the march toward equilibrium. Entropy did not merely govern stars and engines. It governed the very geometry of space-time. Meanwhile, the cosmic microwave background continued to serve as a thermometer of destiny. Each new generation of satellites, COBE, WMAP, Planck, mapped its subtle ripples with greater precision. These maps became a window not only into the past, but into the entropy budget of the cosmos. They told scientists how matter was distributed, how galaxies formed, and how the universe was unfolding. The evidence was clear. The universe was expanding, cooling, and diluting. The arrow of entropy stretched unbroken across billions of years. And then, in the late 1990s, came a revelation that pushed the endgame into stranger territory still. Two independent teams studying distant supernovae found that the universe's expansion was not slowing under gravity's pull, but accelerating. Something unseen, a repulsive force embedded in spacetime, was driving galaxies apart faster and faster. They called it dark energy. Its nature remains one of the greatest mysteries in science. It makes up nearly 70% of the cosmos, yet it cannot be seen, touched, or measured directly. It reveals itself only in the way galaxies drift away, their light stretched into the red of distance. But whatever it is, dark energy has rewritten the script of entropy. For if the universe is expanding ever faster, then the distances between galaxies will grow into unbridgeable gulfs. Stars will burn in isolation. their light never reaching neighbors. Eventually, each galaxy will become a lonely island, surrounded by darkness, sealed off by horizons that no future traveler could cross. The acceleration ensures that entropy's march will not end in collapse, but in exile. Not a cycle of rebirth, not a steady state of balance, but an endless scattering, a cosmos stretched thin until it is almost nothing. The deeper the investigation went, the more unforgiving the picture became. Heat death was no longer a poetic speculation. It was a physical inevitability, written in the lifetimes of stars. The evaporation of black holes, the cooling of background radiation, and the expansion driven by dark energy. To measure entropy in cosmic terms was to glimpse a future so vast, so silent, that language itself falters. A future where galaxies vanish beyond sight, where the last stars flicker out, where even the black holes dissolve into nothing. And beyond that, only equilibrium. The investigation had begun with steam engines, but it ended in eternity. Entropy was not just a law of physics. It was the destiny of the cosmos. The story of entropy is not confined to the lifetime of stars or the evaporation of black holes. Fair stretches across timescales so vast they defy imagination, ages where the word year becomes too small to carry meaning, where the cosmos drifts into epochs that dwarf the span of all human history, of all planetary history, of even stellar history itself. Physicists divide this vision into eras, as though writing a chronicle of existence long after the present age has vanished. The current epoch, the stelliferous era, is the age of stars. For 13 billion years, nuclear furnaces have burned in their billions, shaping galaxies, forging elements, illuminating the void. But this age is only temporary. Star formation is a fragile process, dependent on reserves of cold gas. One day that gas will run out, galaxies will fall silent. Models suggest that within 100 trillion years, a span 10,000 times longer than the universe has already lived, the last new star will flicker to life. From that moment forward, no new suns will be born. The cosmos will enter the next stage, the degenerate era. In this age, the universe will be ruled not by blazing stars, but by their remnants. White dwarfs, the burnt-out cores of once luminous stars, will glow faintly for quadrillions of years, slowly radiating away their stored heat. Neutron stars, compressed into spheres no larger than cities, will persist in silence, their spin gradually slowing. Black holes will linger at the centers of galaxies, swallowing what remains of matter and light. The degenerate era will be a universe of embers, a cosmos where brilliance has given way to endurance, where what remains is not the drama of creation, but the stubborn persistence of what cannot yet be destroyed. Yet even endurance cannot last forever. Over unimaginable stretches of time, white dwarfs will cool to the point of invisibility, becoming black dwarfs, dark frozen spheres of carbon and oxygen adrift in a frozen sky. Neutron stars will fade into silence. Planetary corpses will wander aimlessly. The universe will grow dim and then dark, but black holes, those mysterious engines of gravity, will still remain. For many physicists, they are the final keepers of cosmic structure, the last monuments in a universe stripped of light. And yet even they are not immune. Hawking radiation ensures that black holes leak energy, losing mass atom by atom, photon by photon. For stellar mass black holes, the timescales are almost inconceivable, 10 to the power of 67 years before evaporation completes. For the largest supermassive black holes, the countdown is even more extraordinary, up to 10 to the power of 100 years. These numbers are so large they almost escape language, greater than the number of atoms in the observable universe. But time itself does not pause. And across such spans, even black holes must fade. The last giants will die with a whisper, their mass transformed into faint radiation that disperses into the void. When that happens, the universe will enter its final chapter, the dark era. A cosmos stripped of stars, stripped of black holes, stripped even of light. Only subatomic particles will remain, electrons, neutrinos, and whatever relics survive the decay of matter itself. Here lies the escalation of the mystery. Does this mean that the fate of all creation is sealed? That entropy must flatten every gradient, stretch every photon into irrelevance, and deliver the universe into the silence of heat death? Or is this vision too narrow, ignoring deeper laws not yet discovered? Some physicists have dared to ask whether the accelerating expansion of the cosmos might alter this outcome. If dark energy persists or grows stronger, the universe will not simply cool, it will fragment. Galaxies will drift so far apart that even the light of their last stars will never reach their neighbors. Each island of matter will vanish beyond the event horizons of expansion. Heat death would be not merely the fading of energy, but the isolation of everything that once was, and still other possibilities lurk. Could dark energy fluctuate, reversing into attraction and leading to a big crunch? Could space-time undergo quantum decay, collapsing into a different vacuum state, rewriting the laws of physics in an instant? Or could the universe's story extend into the multiverse, with new regions of creation budding from the collapse of our own? The paradox grows sharper the deeper it is examined. If heat death is real, then time itself is a path with an endpoint, a slope descending towards silence. And if the alternative fates await, they too imply a finite story, one of collapse, transformation, or rebirth. But perhaps the most haunting image is not collapse or renewal, but stillness. A universe so vast, so stretched, that even the last photon carries no useful energy, its wavelength greater than the size of the visible cosmos. A universe where no engines can run, no structures can form, no thought can emerge. This is not the violent apocalypse once imagined in mythologies. No fire, no flood, no cataclysm. Instead, it is a twilight drawn out across endless years, a silence that follows not from destruction but from diffusion. It is not an ending with drama, but an ending with none at all. To contemplate it is to confront the raw scale of cosmic time. For the human mind, trained to measure by hours, days, or centuries, such spans collapse into abstraction. Yet in the cold arithmetic of physics, these timelines are real. They are written in the laws of thermodynamics, in the mathematics of relativity, in the behavior of matter under gravity and quantum law. The escalation is not merely scientific, it is existential. For to imagine the silence of the last photon is to confront the fragility of every spark that now burns. Every star in the night sky, every galaxy that adorns the heavens, every breath of life on Earth exists only in the brief flare of the stelliferous era. We live in a cosmos still young, still alight, still alive with possibility. But physics suggests that this is temporary, a fleeting blaze before an infinite night, and so the mystery deepens. Is this truly the final destiny? Or are there laws beyond our comprehension that will overturn the verdict of entropy? Does the universe march inevitably toward heat death? Or does expansion hide other fates waiting to be revealed? The silence of the far future is not just a scientific question. It is a philosophical abyss, an image that stretches beyond science into the realm of wonder and dread. It is the sound of time itself unraveling. The cosmos, vast beyond comprehension, carries within it not only the memory of its beginnings, but also the seeds of its potential ends. For all the progress of science, the question of ultimate fate remains unresolved, balanced on the knife edge between mathematics, observation, and imagination. From the silence of deep space arise competing visions of how existence itself may one day conclude. The most widely accepted prediction is at once the most haunting. It begins with entropy, the great ledger of disorder. In the language of thermodynamics, entropy never decreases. It is the measure of energy's drift into unusable forms. Across stars, galaxies, and even black holes, energy flows irreversibly from order into chaos. In this vision, trillions upon trillions of years unfold until every star has burned its final fuel. Every fusion engine falls silent. Every ember of matter cools into darkness. Even the deepest black holes evaporate into faint trickles of radiation. At last, the universe approaches equilibrium, a state in which all energy is spread so thin, so uniform, that no work can be done. No light, no heat, no structure. A cosmos not dead in violence, but suffocated in stillness. This is the heat death. A universe whose final act is silence eternal. And yet another fate lies in the equations. If gravity were to prove stronger than expansion, the universe could one day reverse its trajectory. Galaxies would slow, then begin to fall back inward. The night sky would shift over billions of years as clusters drew closer, collisions multiplied, and the very fabric of space-time contracted. Stars would ignite in furious bursts as matter grew ever denser, until the cosmos collapsed in upon itself, a singularity mirroring its birth. This is the Big Crunch, creation and destruction bound together in a single loop, the Alpha folded back into the Omega. A violent rebirth written in the language of symmetry, but gravity may not hold the final word. Dark energy, the mysterious force accelerating the expansion of the universe, suggests a far stranger possibility. If its strength increases without bound, expansion itself could one day overpower every force of nature. Galaxies would be torn from one another, stars pulled away from stars. Eventually, even planets and atoms would be rent apart. Space-time itself would fracture, unraveling into nothing. This is the Big Rip, a universe torn to shreds by the very expansion that once gave it form. Some theories look not to an end, but to renewal. Perhaps the cosmos is not a straight line toward oblivion, but a circle endlessly repeating. In such cyclic models, each heat, death, or collapse sets the stage for a new Big Bang. Like a phoenix rising from its ashes, the universe may pulse eternally, expansion giving way to contraction, silence giving way to birth. An infinite succession of cosmoses, each unaware of the one before. Though evidence remains elusive, the allure of cycles persists. They offer a vision of eternity not in stillness but in motion. Still more radical ideas point outward, to realms beyond our own. Perhaps our universe is but one bubble in an infinite foam of realities. Each bubble may expand, decay, or collapse in its own way. In this vision, heat death is not absolute. It is local, confined to our own pocket of existence. While one universe fades into silence, another may blaze to life. The grand stage of reality would never darken entirely. This is the realm of the multiverse, where endings are never final, only transitions between worlds unseen. Yet there remains one possibility more sudden, more unsettling than all the rest. The laws of physics themselves may not be stable. What we call a vacuum, seemingly empty space, may in truth be a metastable state, a false vacuum. Like a ball resting on a plateau rather than the deepest valley, the universe could, without warning, tunnel into a lower state of energy. If such a collapse were to occur, a bubble of new physics would expand at the speed of light, rewriting reality as it spread. Atoms, forces, and even space-time would vanish, erased in an instant without warning. In this scenario, the universe would not fade slowly into stillness. It would end with a whisper beyond perception, erased by its own quantum instability. What then is destiny? Is heat death the inevitable consequence of entropy's law? Is collapse, rupture, or renewal waiting instead? Physics answers with probabilities, not certainties. But the contemplation of these endings reshapes the human imagination. For in the shadow of cosmic death, the value of the present becomes clear. Every photon, every heartbeat, every flicker of order in this sea of rising entropy shines brighter against the infinite night. Perhaps the end will come as silence, collapse, or sudden erasure. Perhaps renewal waits beyond the horizon, or perhaps the universe is far stranger still, its story only half told. Until that final act arrives, the cosmos continues, expanding, evolving, and unfolding mysteries that challenge both science and philosophy. Its fate remains uncertain, its ending unwritten, and in that uncertainty lies the most profound truth of all, that existence itself is not a conclusion, but a question echoing endlessly into the dark. To gaze into the future of the universe is to confront a horizon that can never be reached. The human eye cannot see beyond its own cosmic age, yet through instruments of extraordinary sensitivity, fragments of evidence are gathered, clues etched into light, matter, and gravity itself. Science cannot witness the end of time directly, but it can trace its shadow across the present, inferring destiny from whispers left behind in the fabric of space. The first and perhaps most profound tool in this quest lies in the faintest of signals, the cosmic microwave background. It is not light from stars nor from galaxies, but from the universe itself, a fossil radiation, born 380,000 years after the Big Bang. When the cosmos cooled enough for atoms to form and photons to travel freely, for billions of years, this ancient light has crossed the expanding void, stretched by time until it glows not in visible colors, but in microwave frequencies. It is uniform yet not perfect. Its subtle ripples carry the fingerprints of the first structures, the seeds of galaxies and clusters. Missions such as COBE in 1989, WMAP in 2001, and the Planck satellite in 2009 mapped this cosmic afterglow with ever-increasing precision. They revealed not only the distribution of primordial heat, but also the density of matter, the rate of expansion, and the very geometry of space. In its pale, silent glow, the fate of the universe is encoded like an ancient script. Yet the story of cosmic destiny was unsettled by a discovery at the turn of the millennium. Supernova surveys, measuring the brightness of exploding stars in distant galaxies, revealed that the expansion of the universe is not slowing, but accelerating. Something unknown was pushing space-time apart, a force now called dark energy. To unravel its nature, astronomers turn to multiple tools. They study baryon acoustic oscillations, faint ripples in the distribution of galaxies, echoes of primordial sound waves in the plasma of the young universe. They chart the positions of millions of galaxies, searching for subtle distortions that betray the hand of dark energy. Soon, the Euclid telescope, launched by the European Space Agency, will extend this work. With sweeping vision, it will probe billions of light-years, measuring cosmic acceleration with unprecedented clarity. Each data point narrows the possible fates of the universe, whether endless expansion, sudden rupture, or cycles unimagined. Peering deeper still, the James Webb Space Telescope lifts its golden mirrors toward the earliest galaxies. In their ancient light, astronomers glimpse the universe's childhood, an age when expansion first shaped structure. By comparing the faint glow of those distant galaxies with models of cosmic growth, Webb tests whether the laws of expansion remain constant, or whether hidden physics may yet alter the universe's trajectory. Every faint arc of light, bent by gravity, every spectral line stretched by expansion, becomes another clue. Through Webb's eyes, humanity confronts the delicate scaffolding of time itself, but the destiny of the cosmos may hinge on scales smaller than atoms. At CERN, the world's most powerful particle accelerators smash protons together at energies approaching those of the early universe. In the debris, physicists test the laws of the quantum vacuum, the invisible sea of energy that underlies reality. The Higgs boson, discovered in 2012, carries profound implications. Its mass suggests that our universe may rest not in the deepest possible vacuum state, but in a precarious false one. If so, the universe could one day decay, collapsing into a lower energy state and erasing all structure in an instant. Particle physics cannot yet confirm or deny this fate, but every collision, every fleeting particle trace, refines humanity's grasp of whether the cosmos is stable or only temporary. Another window has only just opened. In 2015, the Laser Interferometer, gravitational wave observatory, detected the ripples of space-time itself, generated by the collision of two black holes more than 1 billion light-years away. Since then, gravitational wave astronomy has begun charting the hidden lives of compact objects, black holes and neutron stars. Each detection confirms that black holes do not remain forever. They merge, radiate, and alter the cosmic balance of energy. Future instruments, such as the space-based LISA mission, may even detect the faint gravitational murmurs of the early universe, offering direct evidence of processes that shaped its future trajectory. By listening to the universe, rather than only watching it, science broadens its vision of cosmic destiny. No telescope, however, can watch the universe for trillions of years. To probe that unreachable scale, physicists turn to simulations, digital universes governed by the laws of thermodynamics and relativity. They watch as galaxies fade, as stars flicker out, as black holes evaporate. They follow entropy's march across aeons, witnessing in compressed time the approach of equilibrium. These simulations cannot reveal the future with certainty, but they test scenarios: heat death, collapse, renewal. They show what becomes of matter when time itself is stretched beyond human imagination. And they confront scientists with the paradox of their work, studying events that no living observer could ever confirm. For in the end, no device can watch heat death itself unfold. No satellite, no particle detector, no gravitational observatory can span the final trillion years. All that science can do is infer. It pieces together the evidence, the radiation left from the beginning, the expansion seen in galaxies, the particles glimpsed in accelerators, the waves of gravity crossing the void. It stitches these clues into models, into laws, into visions of the far future. But always there remains a boundary between prediction and certainty. Between what can be measured and what must be imagined. The instruments of science are like lanterns in a cavern, vast beyond measure. Each beam illuminates a fragment, the echo of the Big Bang, the pull of dark energy, the fate of collapsing stars. But the cavern itself stretches into darkness unending. In that darkness lies the mystery of the universe's fate. Heat, death, collapse, rupture or renewal, science tests, narrows and refines. Yet no measurement will ever grasp the whole. Perhaps that is the final truth of cosmic inquiry, that knowledge itself is an asymptote, approaching but never touching the infinite. And that in the act of seeking, humanity finds not only answers but meaning. The story of entropy is not merely a tale of physics. It is also a mirror, reflecting the condition of life itself. Every creature, every mind, every star burns with finite fire. The law that governs galaxies is the same law that governs breath, the steady transformation of ordered energy into diffused heat. The fate of the cosmos is written into the fate of the body, the arc of a civilization, the span of a human heartbeat. To contemplate the heat death of the universe is therefore to confront mortality on the largest possible scale, recognition that not only individuals, not only species, but the very stage on which existence unfolds is impermanent. The universe itself is contingent. It was born. It will end. What then becomes of meaning? If the march of entropy ensures that all stars will gutter, all galaxies will fade, and all thought will vanish into silence, what is the weight of memory, of art, of knowledge? From the standpoint of physics, the answer is merciless. Entropy does not preserve, it erases. Every book, every painting, every symphony is no more durable than the fuel of a star. Even atoms cannot hold forever against the dissolution of time. And yet within that abyssal truth, a paradox blooms. For it is precisely because the universe tends towards silence that the brief emergence of life acquires its gravity. A fragile flame burning in the darkness is not diminished by its transience. It is defined by it. The brevity of light is what makes it luminous. Across cultures, humanity has long wrestled with impermanence. Buddhist philosophers described life as a wave arising and dissolving, no less real for its passing. The Stoics of Greece urged the embrace of fate, finding dignity in the finite. Modern cosmology extends this meditation to a scale beyond imagination, the rise and fall not of kingdoms or lives, but of space-time itself. And still, even here, beauty emerges. The universe, though destined for equilibrium, spends its youth in creativity. It fashions galaxies, sculpts stars, carves out the long chain of chemistry that leads to consciousness. In the cold mathematics of entropy, a strange generosity resides. The very laws that ensure eventual death also allow the fleeting brilliance of life. Perhaps then, heat death is not the annihilation of meaning, but its transformation. What seems like silence may be only a frequency beyond human hearing. What appears as the extinguishing of stars may be but a shift into a mode of existence too subtle for matter-bound minds to conceive. Physics cannot claim this. It can only describe the approach of equilibrium, the diffusion of usable energy. But philosophy allows the imagination to stretch further. If time and space themselves are transient, perhaps meaning is not abolished but transfigured, escaping into dimensions where entropy has no dominion. And so, one may envision the future as a cathedral of darkness. Its vaulted expanse stretches beyond measure. Its pillars are the remnants of galaxies long dissolved. In this cathedral no choir sings, no flame burns. Yet once, briefly, the halls were filled with light. Billions of stars ignited like candles, illuminating the immensity with color and warmth. Those candles are finite. They will one by one go out. But in their brief glow they revealed the shape of the universe to itself. They made possible the eye that sees, the mind that contemplates, the voice that tells its story. To know that the stars are dying is not to despair of their light. It is to cherish it more deeply, as a pilgrim treasures the single flame in a vast empty sanctuary. And so the story circles back to humanity, not in arrogance, but in reflection. If the universe's end is silence, what is the role of those who live before the silence falls? Perhaps it is not to fight entropy, for that is impossible. Perhaps it is not even to hope for cosmic renewal, for that remains speculation. Perhaps it is simply to listen while the music of creation still plays, while galaxies still spin, while oceans still move beneath the pull of moons, while minds still awaken to wonder. For in that listening lies a form of resistance, not against physics but against forgetting. Every poem, every equation, every act of love is a way of leaning into the music, even as it fades. The silence may be inevitable, but the song was real. And in the vast cathedral of time it was enough. The stars fade one by one, like candles extinguished in a boundless night. But their brief illumination was enough to reveal the mystery, that out of nothing something arose and for a moment knew itself. And so the closing question remains, whispered across the silence of future aeons. If the universe ends in stillness, is our task not to rage against it, but to listen while the music still plays,